In this video, we're going to cover solving energy balances in which you have mixing. So this is different from energy balances where you don't have mixing. Those you can just do a straight energy balance and find whatever terms you need, provided that you have enough information to solve the balance. In energy balances where you have mixing of two or more components, you may also need to include a mass balance to see, okay, what mass is coming in, what mass is coming out, what's being mixed, do I have a change in, for example, solids concentration, what's my temperature change, what's my new specific heat of this mixture. So it gets a little bit more involved with what specifically is coming in and coming out. Let's take a look at how that works. Here we have a problem where we're mixing ice cubes and lemonade. So right away we know that we've got two things that are mixing, the ice cubes and the lemonade. So when we mix them together, we have some kind of ice lemonade mixture, but then we see that the final temperature of the mixture is 5 degrees C. So that we know when we're doing this energy balance, ice has a melting point of 0 C. So we're going to have a phase change that we need to account for. So let's remember that when we get to our energy balance. What we want to find out is how many kilograms of ice cubes were added to the lemonade. That's what we need to figure out. So we'll do an energy balance to figure that out, and we may also need to do a mass balance because we're mixing ice and lemonade. All right. So we're given some more information about specific heats of the mixture, the ice and water, and the heat of fusion of water. We were also given the specific heat of the lemonade. We're given the initial temperatures of the ice cubes and the lemonade, and we're given the final temperature. So let's go ahead and set up our energy balance and see if we actually do need to do a mass balance. But before we get started with our energy balance, we need to draw a diagram to make sure we understand what's coming in and out of our system. That's going to make the balance a lot easier to write. So we'll start by drawing a little container where we are mixing. We are mixing lemonade, we'll call it L, with ice, and we'll call that I. What's coming out is our mixture of ice and lemonade, so we'll call that M. Now, we have our diagram. We know we're going to have two terms on the inside of our energy balance and one term on the outside because that's what our arrows correspond to. So let's get that energy balance set up. We're going to start with our lemonade term. So that is a mass of our lemonade, the CP of our lemonade. And now, when we write the temperature for the lemonade, we know the initial temperature of lemonade, but then lemonade doesn't come out. So to basically force our delta T, we write the temperature of the lemonade, and this is lemonade coming in, minus our reference temperature. And the reference temperature is just to set an equivalent basis, whether we're in Celsius or Kelvin. So that's how we are creating our MCP delta T term for our lemonade. Now we have the ice. So we have the mass of our ice, the CP of our ice, and the temperature of our ice. Now we have to think about this pretty carefully here because we don't have ice past 0 Celsius, but we know the final temperature of the mixture is 5 Celsius. So when we write the temperature of ice, we have to say, okay, we know we are starting with a certain temperature of ice, but then we can only heat it up so far until we no longer have ice. So if we're heating our ice up, we can only heat it up to 0 C. So that means our temperature term for ice, we are going to start with the initial temperature of the ice. We'll subtract our reference temperature, but now we need a term that accounts for the ice melting, and then that water that we now have, that's the ice melt, is heating up the rest of the way to 5 C. So to account for our phase change, we need mass of the ice, and that is times our latent heat of fusion. So I'm going to write that as delta HF. Okay, so far we've heated the ice up and we've melted it, and now we have water. So to finish our ice terms, we now have to have the water. It's still your mass of your ice, but it's now water. Didn't change mass, it just melted. You have the CP of water now, because you're dealing with a water term, and now you are actually going up to the temperature of your mixture. So I'm going to write this as Tm minus your reference temperature. And that takes care of the inside. So when you have a phase change, you need to account for the phase change and then any subsequent heating after your phase change. Now that we have done the inside, we can take a look at our outs. And so we only have one term coming out. We have the mass of the mixture, the CP of the mixture, and the temperature of the mixture. And when we do that, again, we are going to use our reference temperatures, like so. That is our energy balance. So let's go through here and see what terms we have and what terms we don't have. We have the mass of the lemonade. We're given that. We have the CP of the lemonade. We have the initial temperature of the lemonade, and we know our reference temperature. So that particular section is taken care of. We don't know the mass of the ice, but we do know its CP, and we know its initial temperature. So we're okay there. Again, we don't know the mass of the ice, but it's the same as before, so that's still only one unknown. We're given the heat of fusion, so we're okay there. We're given the CP of water, and we're given the final temperature. So all we don't know on our inside is the mass of our ice. Now let's take a look at the outside. We don't know the mass of the mixture. We don't know how much ice is added, so we can't figure out what the mixture is yet. We do know the CP though, and we do know the temperature of the final mixture. So because we know only one mass here, we are going to have to do a mass balance. We have two unknowns in this energy balance. So we need one more equation to be able to solve for that. And fortunately, it is a very, very simple equation. It is the mass of your lemonade plus the mass of your ice is equal to the mass of your mixture. Simple enough. Now, we are trying to figure out how much ice we add. We really don't care about the total mass of the mixture. So what I'm going to do is rewrite the energy balance and replace the mass of the mixture with what it's equal to, the mass of lemonade plus the mass of the ice. So when it's all done, the equation looks like this. The next thing we want to do, now that we have this entire long equation written out, we need to solve for the mass of the ice, which means we need to get all of our ice terms on one side and all of our other terms on the other side. Now I'm going to work in Celsius too, so that means all of my reference temperatures are 0. So in this next step, what I'm going to do is pull all of the ice terms to the left of the equal sign, all of the other terms to the right of the equal sign, and since all of my reference temperatures are 0, I'm just going to get rid of them. They all go away. So here's what this looks like when we're done. There we go. Okay, now what I'm going to do is scrunch my terms down a little bit. So I pull out mass of the ice on the left side. Everything else is multiplied by that, so I can collect all those terms together. Mass of the lemonade is on the right side, so I'm going to pull that term out and collect the other terms together. So let's shorten this up a little bit. There. That looks better. All right, the final thing we need to do to get the mass of the ice by itself is to take that huge term in the parentheses on the mass of ice side and divide through by that so it ends up on the right side. Let's do that. And that's our final equation. So when we crunch through all these numbers and we solve for the mass of ice, the mass of your ice is equal to about 0.86 kilograms. Now, key thing to keep in mind when you solve this problem, first, when you plug in the temperature of ice, that needs to be -10. Yes, I know that it will make your term negative, but you have to start with -10 because that's your temperature. If your temperature was 50, you'd put 50 in. So just because there's a minus sign in your temperature doesn't mean you need to drop that out before you put it in. Put in -10 right in for TI. Second key thing, your heat of fusion. You are melting. So your heat of fusion is negative. So when you plug in for delta H, you need to plug in negative 333.6 kilojoules per kilogram. That is the only way you are going to get the mass of ice that is not negative. If you leave out that negative sign, you're going to get a negative mass of ice. So if you keep your signs consistent and you input the information that the problem tells you to, you end up with 0.86 kilograms of ice. Which means if you wanted to figure out how much mixture you'd had, you would just add 0.86 to 5 kilograms, which is how much lemonade you had, and you get 5.86 kilograms of the mixture. And there you have it. So that's solving energy balances that include a mass balance as part of the problem. If you'd like to solve just an energy balance, no mass balance included, check out the video Solving Energy Balances 1. That's just a straight energy balances and no mass balances. So with those two videos, you'll see both types of energy balance that you can solve in Introduction to Food Engineering.